Hey Victoria,
Hi Sarah, how are you?
I'm good. How are you?
Good. So, um, what do you need help with today?
I just wanted to just review acids and bases again. I practice a lot on it, so I'm kind of like I feel like I'm doing good, but sometimes
Okay.
don't like when there's like an inductive, that's where I get confused.
Okay. Okay. Um, so you just have to memorize some of them.
Getting the inductive part, induction.
Yeah. Let me see. Let me see what your teacher has. Do you have any notes on this? I think this was just acid basis, right? Mm, these resonance. Okay, well, I'm just gonna. Because inductive effect, all it means is just that it's donating electrons or pulling electrons, right?
Yeah.
So it just means that it's a very polar molecule. I don't know if your professor has any inductive effect information here.
Um, I think the first first example for acidity. So it's on page, let me just count 1, 2, 3, 4, 5, 6. On the seventh page?
Page 7
Hmm.
on this one.
Oh, wait. Is this a different? This is a different packet, I think. Which one am I using? Oh, no. It's not this packet. My bad. But these are all just practice problems, I guess. Yeah. I don't know. I have another one.
Okay.
Um,
Are you going to send me the other one or are you just
I'll open it.
okay?
It's more easier. Let me just.
Let me stop sharing then.
Mhm. Spaces.
Because inductive effect just means like polar. That's all literally, that's what it means. It just means that one side is more negative than the other side, and one side is more positive than the other side. And that's what's triggering the electrons to move one way or the other. And that's why we end up with resonance. So
Okay.
inductive effect ends up with resonance effect, and then we even end up with what is it? hyperconjugations. That's all it means.
Okay.
So if you are looking at a very electronegative compound, for instance, like nitrogen and oxygen, like nitrates, that means that they are very negative. I mean, that they have a very large inductive effect because they are either electron withdrawing or electron releasing.
For inductive?
For inductive effect, yeah. Because inductive effects can be either electron withdrawing or electron releasing.
Okay. If I we can do this problem, and I think there's an inductive in this, which I think it's
the fluorine. Yeah.
fluorine.
So fluorine in this scenario, it's an electron releasing, right?
How do you know it's electron releasing? That's kind of confusing.
So electron releasing just means that when fluorine leaves, fluorine is going to take that electron. So then that carbon in the center, let me do the annotation thingy. So this carbon is going to end up with a carbocation, right? So that's why it's a electron releasing. So think of it as this. Inductive effect. There's two types, right? There's the electron withdrawing and then electron donating or releasing. Okay, so electron withdrawing is negative and electron donating is positive. Okay, it's a positive inductive effect. Okay, so if you have like NO2, this is going to be more positive than this, which is going to be more positive than this, this, this. And then like esters or alcohols, right? And then we have benzene. And then we have hydrogen and then methyl carbon. Oh, I can't write there. Okay. So think of this as 0, okay? Okay, it won't let me write any further than that. Okay. Like, what is it? CH3C, okay, which CH3CH, which is larger than CH3CH2, which is larger than CH3. So all of these, as you go more this direction, we call these electron withdrawing. Okay, and as you go towards these, they become electron
Donate.
Yep. I like the positive effect. Okay. That's all you need to know. There's nothing else to this.
Okay.
Yeah, it just means that, for instance, like it's bonded to this, right?
Mm.
You know, this can leave as an F minus. So then what happens to the carbon? It becomes partially positive, right?
Mhm.
So this has a partially negative and this has a partially positive. That's what inductive effect is, or polarized means.
Got it. Okay.
Okay, that's it.
And so when I do the okay, so I got the inductive. So when I'm doing the like acidity or basicity,
Hmm.
uh, and you figure out the stability through
Hmm.
per, so whichever one, like whichever one is like polarizability, that's more stable, making it more acidic. And is that the same thing for basic? If like
Yeah.
there,
Hello?
yeah, because sometimes like I thought maybe I was like doing the opposite for base. So I kind of get confused, like what's the difference between acidity and basicity when I'm like trying to figure out the increasing.
So it
Which one?
really depends on which acid and base you're talking about. If it's Lewis acid and base, it's going to be a little bit different from that of Bronson-Lowry acid and base, right?
Mhm.
So in Orgo, there's not just one type of acid and base, there's multiple types of acid and bases, and you just have to figure that out. But
Okay.
yeah, but if it's a base, Bronson-Lowry base, right? The weaker it is, stronger the Bronson-Lowry acid, which means more stable it is, right? But if we're talking about Lewis acid and base, and the Lewis base is the one that's donating electrons, then the more able to donate electrons, it means that it is electron withdrawing, right?
Mhm.
And if it's electron withdrawing and there's a potential of resonance, then that's more stable. You see what I mean?
Yeah.
So you just, at first, you have to establish what type of acid and base you have.
Mm.
So this is why like Orgo becomes a little tricky. It's not like Gen Chem where there's like rules and you just have to memorize it. You actually really have to do some critical thinking, unfortunately.
Okay.
Yeah.
So is it okay if we like practice more? Cause like in the beginning, like once like when I figure out which one is acid or like base, depending on the
Mm.
charge,
Mm-hmm.
like then I get confused. Like after, like when I'm doing like distinguishing them like after per high. So maybe the packet that you opened, can we go back to that and then just like, because sometimes I feel confident, sometimes I don't. So
Okay. Oh, my screen just. Okay. Sure. Just, do you want to go over these, the ones that your
yeah,
teacher gave
yeah, yeah,
you?
yeah.
Oh, okay.
Yeah, because I wasn't able to complete all of
Okay.
because I got confused.
Yeah.
So like on the at the very bottom, not these, the ones that are like at the bottom. Yeah, yeah, yeah. The ones that are asking like basicity or acidity.
Okay. Yeah.
And then it also asks for the including mechanism arrows, and I didn't realize that I had to like know that. So just fix this.
Okay. Do you want to try this one?
Yeah. Make the blood makers acidic. Oh, I have to annotate. So they're all hybridization. And would there also be like resonance?
Yep, there would be resonance, but not all of them would have resonance, right?
Hmm. Yeah, that's where I get confused.
Okay, so wait, this one right here, it should be this. Oh, not that. It should be this, right?
Yeah.
So we have a carbon here and a carbon here and a carbon here, right?
Mm-hmm.
So this carbon is only one carbon away from benzene, so like at the end of the day you can have resonance, right? But this one right here, you cannot have resonance. And that, yeah, and that double bond should be here, but the lone pair should be there.
Mm-hmm.
And then this one, yes, you can have resonance, but the resonance, yeah, that one can have resonance. So you know what I mean?
Mm-hmm. So the first and the third one have resonance. The second one doesn't have resonance, so that would be a weak acid.
Yeah.
That would be the weakest.
Yeah.
And then, and then how do you compare the first and the third one then? Since
We
both
have
of
to
them.
look at the resonances, but which one is more accessible? Which one is going to be a stronger base? Like which one is more able to accept protons? Then that's the weaker acid. You know what I mean?
So that the first one is
I
stronger.
think so. Yeah.
Okay. What about the hybridization? Do we just ignore that because all of them have hybridization?
Yes.
Okay.
Except for this one doesn't have this one doesn't, the second one didn't have hybridization effects, you know, for the hydrogen that it took out, because they wanted to take out that last hydrogen for this one, right?
Mm-hmm.
You know what I mean?
Mm-hmm. When we're doing Perhi or Perhi,
Yeah.
Do you look at where the electron is placed on?
Yeah.
Oh, okay,
Because
so if
I think
if
I think that's what your teacher is asking you to do. I've never heard of Perky before. I think your professor is just making you guys understand that acid and base
making us do
depends on,
what? I can't hear you clearly.
your professor is helping you guys understand that acid and base is not just one. You know, it's not just one factor that affects acid and base, but it's multiple factors. And those factors are per-Hi or per-He.
Oh, okay.
Yeah, so that's something that your professor made up, it's not in the books.
Oh, okay.
To help you guys understand. Yeah.
It's just that he wants us to like show our work, and show the per-He method, I guess, like so that I just want to get it down. And so when I'm doing the per-He, I look at where the electron is placed on. So since the electron wasn't placed over here, that's why it's not hybridization. It was placed here.
Say that again?
So where the charge is where I look at for polarizability, electronegativity.
Yes.
Like per-He.
Yes.
But since the charge was not here, it was not here, but it was here for this one.
Yes.
That's not hybridization.
Yes.
Oh, okay, so that makes so much sense now. I don't look at, that's why I get confused with hybridization, because I see that, oh, that's hybridization, but I always forget that no, there's no charge there.
Mm-hmm.
Okay. Can we make it to like another one?
Yes.
So, acidity. Most acidic.
Mm-hmm. Why do you think the second one
negative.
is most acidic?
Because it's charge.
Because it has a positive charge?
Yeah. Because it means charge and the other ones are neutral, I think. Wait, yeah, they're neutral.
I don't think the middle one is most acidic just because it has a positive charge. I would say that the third one is most acidic because of resonance. Because it's stabilized by resonance. You see that?
So the third one would be more acidic because it's stabilized by resonance?
I would say so.
Okay.
And plus positive charges, they destabilize in regards to electronegativity. And resonances, you have to delocalize through the space, right? So delocalization of the charge will make it more stable.
If you don't mind, can you like do this step by step so I can like see how I should actually do it instead of like
this is resonance, right?
Mm-hmm.
Okay, out of per-He, this is going to give you resonance, right? What is this going to give you out of Perky?
Connectivity.
So all of them are electronegativity because nitrogen is more electronegative than hydrogen, right? So all of them have electronegativity. Because the charge is on the electronegative atom, right? So the fact that it's positive on the nitrogen, this means that it's very unstable. Because electronegative atoms, they want to have negative, not positive, right? So I would say that this is the least acidic. And this one has, I think this is the heat part. The hyperconjugation. Because it has no charge, but it's still an S character because this is sp3.
So this is hybridization?
I think so. Hyper, or what is the H part? Hyperconjugation?
Can you repeat that?
I'm asking you what the H part is in Perky.
Oh, it's hybridization.
Oh, it's not this, right? It's hybridization, right?
Yeah.
This
and
is
then
polarizability, electronegativity, resonance, and hybridization, right?
and then I is there for induction.
I is induction. Okay. I think this is hybridization.
Okay.
Induction. Yeah, because this one is right now the most stable, but it's more stable than number two. Number one, this one is more stable than this.
Mhm.
And then resonance is the most stable. So I would say this is most acidic, second, and then third. That's how I would do it.
Okay.
Okay. Do you want to try this one now? This is nitrogen. Okay. Okay. This one's actually really easy. I think you can do this one. What did you write here? Sarah?
Oh, sorry, I was mute.
Oh,
So I wrote that this one is most acidic,
I don't
and
think so.
and this is less. Well, actually, no, this one is the. Yeah, this one is less acidic. And this would be second. So,
you don't have answer keys to this, do you?
wait, actually, I think I do. Let me just check.
Okay. Because I don't think.
Let me check the answer key. Acids,
Because I think these two are more stable than this. This is going to be the least acidic, in my opinion. Because this negative is sitting on a carbon versus this negative is sitting on a nitrogen and this negative is sitting on a nitrogen. Nitrogen is a lot more electronegative than carbon.
yeah, that makes sense. Mm-hmm.
So if that's the case, the second and the third molecules are going to be more acidic. Now, because both of them are nitrogen and electronegative nitrogen, and nitrogens are both electronegative, right?
Mm-hmm.
They're electronegative atoms. So based on that, because they kind of cross out in the electronegativity kind of equals each other out, right? Polarizability would also equal each other out because we definitely know that one side is going to be negative, one side is going to be positive. Now we have to look at resonance. Which one is more likely to have resonance, the second or the third?
The second one.
Good. So I would say the second one is the most acidic. Does that kind of make sense?
Wait, can you say that again?
I would say the second one is most acidic because of resonance.
Mm-hmm.
The third one doesn't have resonance.
So second one is most acidic,
Mm-hmm.
then the first one, and then the third one is
Least
least.
acidic. Yep. I would say 1, 2, and 3.
Okay.
Does that kind of make sense? Yes.
Yeah, it's making sense.
Do you want to try this one now?
I can't erase my work.
All you have to do is just, when you go to annotate, you can, do you see like erase? If you hover over erase.
Yeah.
I got it.
Oh, that's so weird. I thought. Okay.
It's okay.
Let me try for this again. Can you like zoom in a little?
What?
Can you zoom in a little?
Oh, yeah.
Mm.
So this one, they're asking you to add a proton, right? Because it says you may use HA as a generic acid. Do you see that?
Yeah.
I'm assuming you can add it to the nitrogen is what they're asking you to do. And they're asking you to rank it the following by increasing basicity.
Mm-hmm.
So this is if you add, huh?
Yeah.
Oh, I thought you said something. Then this becomes positive, right? And if you add another proton, this also becomes positive.
Mm-hmm.
Add another proton, this also becomes positive. So in PERHI, polarizability would definitely be there. Electronegativity would also be there because they're all electronegative, right? So now we have to look at resonance or hybridization or induction.
Mm-hmm.
But there's one that has inductive effect.
The middle one?
No.
The third one?
Yes. The oxygen is pulling that electron. You know, the oxygen is electronegative. So this is going to give you inductive effect.
Mm-hmm.
Right? So if you have inductive effect, is that stabilizing or destabilizing?
Stabilizing.
Good. So that's probably going to be the strongest acid or the weakest base, right?
Yeah.
What about the other two? This one also has to do with inductive effect. Do you know why? Look at that.
So that would be second increasing base. And then the first one would be the least.
So yeah.
Wait, so if it's inductive, like in base form, if it's inductive, it's the most basic or
No.
the least?
You have to figure out what type of inductive effect this has. Is it positive or is it negative? Is this methyl group giving you electron withdrawing or is it electron donating? This one is electron withdrawing because it's pulling electrons, right? Because oxygen is very electronegative. It's pulling electrons, so it's electron withdrawing. But what about this carbon right here?
It's not.
What is it? It's electron donating, right? So do you see how because this is electron donating and the nitrogen is positive, they kind of balance each other out?
Mm-hmm.
So they become stable.
Okay.
Do you see that?
Yeah.
Versus this one right here, the third one, this is electron withdrawing. It's pulling electrons. So I would say this is the weakest base because this is the strongest acid. And this, so this is, oh, increasing. So this is 3, this is 2, and this is 1.
Okay. So when it's electron donating, that's when the base is the strongest.
If there's a positive charge somewhere else, right?
Mm-hmm.
You have to look at the positive and the negatives. Okay, let's look at this one then. This is also an increasing basicity.
So when a molecule has a more resin structure, meaning it's acidic, but here it's base, so the first one would be least basic because it has a resin structure.
Yeah. Yeah. But see, just try to add a proton though. Right? Try to add a proton because that's what you're supposed to do with acid and that, I mean, ranking bases. That's what they're saying. You may use HA as a generic acid. If you do that, this is positive, this neutralizes, right?
Mm-hmm.
Okay, so which one do you think is
The third would be more basic.
so obviously this is the weakest, right?
Mm.
I would say the third is most basic too.
And the second would be second.
Okay. What about this one?
The charge. Wait, let me just.
So remember, usually if it's a large atom, it's supposed to be most stable.
The middle one is more stable.
For acids.
So it'd be the least basic.
I think so.
And the third one would be, so the first one would be more basic then, most.
I think so. No. This one has to do with electronegativity. Which one is more electronegative?
Oxygen.
Okay.
And the nitrogen would be third, the weakest.
So acid-wise, it would be like this, right? So then base would be the opposite.
So the strongest acid would be the weakest base.
Right. Because these are all Brunson-Lowry bases that they want us to rank.
Yeah. And then the third one, so the middle one would be weak acid. And the third one would be the strongest acid. I'm sorry, strongest base.
The middle one would be the weakest base, right? Yeah.
Okay. Let me do another one.
Oh, sorry.
This is also okay.
It's also base. Yeah.
So H. So this one is more electronegative. Meaning it's more stable. And okay, that's where I get confused because of the acid and base differences.
Okay. So don't think of bases yet. Just do them as if they're all acids.
Okay, so if this was an acid, this would be the strongest. Strongest.
Yeah, strongest acid.
Yeah, I just.
Chicken scratch.
Yeah, it's hard to like annotate. So
Are
it's
you
strong.
using a stylus?
Yeah, I am, but I don't know, like it's when I annotate on
Mhm.
Zoom, it just doesn't work well. But when I'm like annotating on something else, then it's
Oh. What kind of computer do you have?
I have an HP.
I don't know. I never worked with HPs. Okay.
So like when I'm doing it on Zoom, I step like it just doesn't work right. And when I'm using like the OneNote or anything else, that's where it
Mm.
works. And plus my name comes in the way, so it's hard to like write. This would be the strongest acid. And then these two, that's where induction.
Oh.
And so the
Mm-hmm.
inductive
Yep.
and so this would be second strong
Yeah.
acid,
Yep.
and this would be third
Mm-hmm.
strongest acid. And so in base, this would all be the opposite.
Mm-hmm. So once you have the acids, it's always easier to go back and make it into bases. Does that kind of make sense?
Mm-hmm.
Yeah. I always do it that way just because otherwise I get hella confused.
Yeah, that's why I was also getting really confused. But like now I'm getting like and just because it's easier for me to do the acids and bases.
Yeah, it's always like that because we always learn about acids first, you know?
So this would be the weakest
Uh-huh.
base,
Yeah.
and then this would be second weak base, and this would be the strongest base. So 3, 2, 1, like that.
Yeah.
Awesome.
Mm-hmm. Let's try that one now.
Okay. For neutral charges and acidity, that's the most acidic, or should I just? I always get confused with the neutral charges, though.
I don't think you should worry too much about neutral charges here.
Okay.
Because neutral charges doesn't really tell you much about anything
Hmm.
most of the time. Because neutral charges doesn't the reason why we get confused with neutral charges is because neutral charges doesn't tell us which direction the electrons are moving.
Mm-hmm.
And based on how well the electrons move, we predict if this is an acid or a base, right? Because we're trying to see if this is an electron donor versus an electron acceptor versus
Mm-hmm.
proton donor, proton acceptor, right? So I would always just look at the neutral stuff, kind of like in between, and then I look at other ones and I rank those.
So rank the ones that have charges first and then the
I
neutral.
would. Yeah.
Yeah, okay. Would this also be induction?
The
These
middle
two?
one?
Yeah.
So the first one would not be induction. Only the middle one would be induction because of that second oxygen. Because
Okay.
of that.
This would be the strongest in
That would
acid.
be the strongest acid, yeah.
making it the weakest base.
Correct.
Weakest base. And then these two. Okay, what about the first one?
So it's got a negative charge, and that negative charge, but the thing is, this one, and even, because we're looking at these two, that negative charge is being stabilized by that resonance, right? So in per here, R is out.
Yeah.
Right? R is out, E is out because they're all oxygens, polarizability are all out. So now what are we looking at? Hybridization and induction. And we've already discussed that. So now we have to look at hybridization. Does oxygen like to be bonded to all that?
Wait, can you repeat?
Does
that?
oxygen really like to be bonded to all that? Does oxygen like to be bonded to all of those hydrogens?
No.
Not really.
Mm-hmm.
And I mean, if it does, yeah, it does. But okay, well, first of all, this is a negative charge and protons are positively charged, right?
Mhm.
So this is very likely to accept that proton versus this one. Is it likely to accept that proton? Not so much, right? So in regards to
Wait,
acidity,
why is it like that though? Why is
why is
it
it like what?
why is that hydrogen not making that oxygen upset and then the first one it doesn't?
What? I don't think I understood your question.
Like you said, the upsetting part for hydrogen.
Oh, accept.
Accept. Okay,
Yeah.
accept.
This one will be accepted because its proton's positive and this is negative, right?
Mm-hmm.
Readily accepts. This one not readily accepts, right? By definition, Bronsted-Lowry base means acceptor of protons, right?
Mm-hmm.
So which one is better at accepting protons? 1 or 3? The first one, so this is the strongest. Does that make sense?
Mm-hmm. Yeah.
That's all we're saying here.
Sense.
Yeah?
Mm-hmm.
Okay, cool. Did that kind of help you?
Yeah, it helped a lot.
Okay, great. So I think you should just continue. Just go over the ones that we just did, okay? And then I think you just needed to see that when to use Perky and which Perky to use for each one.
Mm-hmm.
I think that's what you needed to do.
Yeah.
I will upload this on YouTube. Give me like give me a few minutes and I'll just upload them, okay?
Okay.
It takes a little while for Zoom to convert the file into an MP3 file, and then it takes me a while to upload it. So just give me like 30 minutes and I'll upload it, okay?
Okay, yeah.
All right, sounds good. I'll see you I think I see you next Thursday, right?
Yeah.
Yeah. Okie dokie, Sarah. Have a nice week.
You too.
Okay, bye.
Bye.